Today we will start differentiation, numerical differentiation or derivative. So how do I get derivatives numerically? So we will use what Newton said. No, Newton, what is a derivative? I said difference of the function between 2 points and divide by delta x, right. The definition is f prime of x is f x plus h minus f x by h. But in reality we can, in computer we can't make h 0, h tending, h will be small, but you have to choose a finite h, and that is where all this confusion and well, not confusion, approximations come. How good is your algorithm? So I will there are quite a few ways to do it. So right now I will describe something called finite difference. In fact, there is a way to do derivatives using Fourier transforms as well. So that I will do it later. Okay. So when you do Fourier transform, so we will worry about derivative using finite number of points. That is called finite difference. So simple idea is I have 2 points discretized. So let us call it xi minus 1 and xi, and the y axis is a function here and here. Suppose the function is linear, then it is straightforward. No, linear, if this idea will work even if h is finite. For linear function you can just, since slope is constant, so f prime at any point in fact, but I am interested in the derivative at the given points. So all my calculation will be derivative here or here, but derivative is same everywhere, and that is f of, so I am going to put a shorthand. Okay. So f I, it means function value at xi. Okay, this shorthand, in fact is the formulas are a bit long, so we need to make it as shorthand as many shorthand as possible. F I minus 1 divided by h, which is h is, this is same as xi plus xi minus 1. This is good, this is in fact exact. For linear functions this formula is accurate, but if the function is not linear, just imagine that I have a function which is going through these 2 points but like this. Okay. Now this formula is not good, right. My derivative number is this slope, but the value of the derivative at this point is in fact slightly negative. Here it is positive, but it's, so here is at this point is overestimating, at this point is underestimating. So as soon as you put nonlinearity, higher order terms, then this does not work. Maybe what I will try is I will put a midpoint. So let us say that I have 3 points. There are 2 points, let us put 3 points. So I will do it right here, or I can make a new one. So take 3 points xi minus 1, xi plus 1, and we have 3 points. So the function goes like that, right. So what I could say is, well, it's better if I want the value of the derivative in the midpoint. So slope is, real slope is this. So I can take these 2 points, and in fact if I want the slope at the midpoint, I should take the difference of the functions at the 2 adjacent points, and this is better. In fact it is exact if it is quadratic. If the function is quadratic, then I will get an exact formula, f prime of x is f I plus 1 Okay. So, this is better formula, and so I will prove it actually. Why is it better? What is the error? Okay. So, but suppose the function, I mean I want to use more points, like let us say I want to use 4 points. Now this is 3 points, 1, 2, 3. I want to use 4 points. Now with intuition you can't really derive these formulas. So you have to get to some mathematical formalism, and we can again go back to Legendre interpolation, and you can derive what should be the formulas, any order. So I will just illustrate how to get derivative using 2 point and 3 points. You can also use higher order schemes. Okay. So let us just look through this slide, because I do not want to really write, functions are quite long. So the idea is to derive any order derivative with any number of points with Legendre interpolation. That is why I hope you realize that this is a really good framework to derive a lot of numerical schemes, Legendre interpolation, and that is why interpolation is mother of many numerical schemes. Okay. So you have to look at the slide. I did not make a slide, but because typing there and keep I mean PPT also it just takes too much time. So what we will so I have 2 points xi minus 1 and xi. So make a interpolating function or Legendre polynomial which goes through these 2 points. So this is the interpolation, you recall. So it is linear because I am using only 2 points, and using these 2 points I can take the derivative of this function. Now this is a function of x, so I can take the derivative of it. So f prime, just take the derivative of the function. So I will get a term here which will be fi divided by this one, and here also fi minus 1 by this, but both of them are opposite sign. This has opposite sign as that, they are equal but opposite sign. Please keep in mind that these differences need not be equal. So sometimes you keep this large, small, especially near the walls you need to make fine grid, and away from the wall you make a coarse grid. So so if I take the derivative, I mean you can just see that now it turns out that this derivative is formula will be same. So let us just do it for one expression. So f prime of x is fi, I am going to write as h, and next one is fi minus 1, and this will be minus h. So in fact I can put a minus h. This is derivative at any point, but so now there are some notation, we need to understand the notation. I am computing derivative. So this is exactly same formula as what I wrote here. No, it is exactly same. So I derived it using Legendre polynomial. Now if you want to take the derivative here using the point which is to the right, this is called forward difference. So I am sitting here, I am looking towards ahead, so forward. So this is called forward difference and is d plus. So this is an operator, d plus is an operator. This is called forward difference operator acting on f, which is this formula. Now it turns out since derivative is same at any point, so it is the same formula for if I take derivative here and look back. So I gone ahead, but I want to use the point behind me to compute the derivative. So it is called d minus, it is called backward difference, but it turns out both these formulas are equal for this linear polynomial. In fact it is hi, this forward. So hi is defined as xi minus x. So higher of the two, okay. So that is again you have to keep in. So xi minus 1. What about hi plus 1? Will be xi plus 1 minus xi. Okay. So now I want to do better. Now this formula, as I said, is good for linear function, but I want to work out function like this or even higher order polynomials. Then I can look at higher order Legendre polynomial. So I have 3 points. So xi minus xi plus 1 divided by what is the denominator which is missing here. So the first is x minus xi x minus xi plus 1 divided by what? Please do not forget Legendre, okay? Legendre polynomial is the basis of everything. Xi minus 1, xi minus 1 minus xi plus 1. Now, what should this function be? So, if I put x equal xi minus 1, I get 1 and this would be xi minus 1. It is simple. Whatever is here should be here, these two, plus 2 more terms, that has 2 more terms. Now, so this is a Legendre formula. Now, you can take the derivative of this function. So, derivative will be, now I have to take the derivative then compute at given points. So, the 3 points xi minus 1, xi and xi plus 1. So, let us take the derivative of this. So, if I take the derivative, it is a chain product rule. So, bottom remains as it is. So, if I have to apply the product rule, this is remains unchanged and this is 1, this is x is sitting in front, and if I keep this function and take the derivative, I get xi I plus 1. So, I keep this function and take the derivative. Okay. Now, so this is what I will get as the first term. So, I would not write more terms, but now I had to substitute one of the 3 points. So, I want to compute the derivative, this prime is derivative, this one at xi. So, put x equal to xi. You put x equal to xi, this goes to 0, only survives this. So, it is xi minus xi plus 1, which is minus of hi plus 1, there is a minus sign here, it is hi plus 1. And now divide by what are these guys? This is minus hi. So, let us write this one. You agree that if I take the derivative at xi, so above is minus hi plus 1, bigger of the two, divided by now these guys. So, xi minus 1 minus xi is minus hi, and what about this? So, this is hi and this is hi plus 1. So, you have to add them together, it is this difference. So, minus minus becomes plus, I am going to remove as hi plus 1. Okay, so, this is the first term and fi minus 1 of course. So, we can do the same thing for next 2 terms, this term and that term. So, you get this. So, this is the formula for the derivative where at the midpoint. Okay. This is called central difference, you are doing at the midpoint, that is called. So, this is central difference and the expression is given here. Further is a nice book which has these details, derivation, but I have put it here. So, you can just look at it. Now, if I put the case when hi, so if this difference are equal, then the formula becomes simpler. There are cancellations, in fact, this term will cancel, right, I mean this term will definitely cancel, and you get a pretty simple formula which is this fi plus 1 minus fi minus 1 by 2h. Do you see it on the board? It is, where is it? I erased it. For this, this is the one. This is exactly same as what is there. So, we have derived it mathematically. Now, we can also compute derivative. So, this is the derivative computed here. What about derivative here? How will I do it? So, I have derived this derivative, this function. Now, substitute x equal to xi minus 1 and you get a formula, okay, and the formula is this. Okay. Now, please do not expect me to do it, you also probably not do it. SymPy is good thing, actually SymPy could do it, I mean we will just give the answer, all the algebra will be done by SymPy. If you are interested, you can write it and you should get the answer. So, this is the formula for f prime xi minus 1, this is xi plus 1. So, this will be forward difference with 3 points and this will be called backward difference. So, you have 3 names, forward difference, backward difference and central difference. Now, suppose somebody says what is the second derivative, you will need second derivatives on many physics problems, no Schrodinger equation, they are second derivatives. So, how will I compute the second derivative? With 3 points, with 2 points what is the second derivative? With just 2 points, 0, there is no second derivative. So, you need at least 3 points. So, how will I do it if I want to do second derivative? Double, just do it twice. So, use this function Legendre this fx, this one, and take derivatives twice. So, I have to take the derivative second time, and if I take the second time, this is becomes 2, right, one here and one here. So, just do it twice and you get the second derivative, and I will just, so is it clear? I mean, this is quadratic, straightforward. In fact, coefficient of x squared, you just put 2 and you will get the answer. You do not need to worry about the linear term, they will all vanish. So, that second derivative is easy, and it turns out this is a formula. They do not look very nice, no, they do look ugly. So, I will give a table where you can read off from the table. So, this is a formula for the second derivative. Now, when for equal interval, when hi plus 1 and hi are equal, then it simplifies a bit, and this is a formula. In fact, this formula you should memorize, okay, you will need for your homework and projects, definitely you will need this. If you are doing, well, most of the projects are based on differential equations. So, this is a formula. So, what do I do? So, add the values of the function at these 2 points, and subtract twice in between. You can also do this by compute the derivative here and derivative here, first derivative, and subtract off. You will get the same formula, okay. But this is, I have derived it here for Legendre polynomial. So, now all this derivation is, if you want derivatives with 3 points, you can't derive it at every time. So, there is a table, and let us see how to understand this table, and also gives the error. So, I will basically tell you a little bit how to compute error, but let us first understand what this table means. So, we have 5 points, so let us write it here. So, I have, there is a I minus 2 as well, right. Okay. So, I want to compute function at, so at, so the formulas, I will not block them, I want to do it here at I. So, that means I want to compute my derivative at point I. So, what is the forward difference using 2 points, which is fi plus 1 minus fi. So, that is, this should come with a minus 1 sign, this should come with 1 and divide by h. So, h times f prime I is fi plus 1 minus fi. It is easy to read. Now, this table you should really use it. Now, somebody said, well, I want with use 3 points, but I want to compute derivative here. Now, this we already derived before. Okay, so, let us look at which formula I should use. So, I had the points, of course, my points were I minus these 3 points. Okay, but so you should just see that I am using a derivative here. So, 2 in the right. So, there is a forward difference, and the formula which I mentioned it, I am sure this one. So, using the points ahead of you. So, the point at where you are is minus 3, then 4 and minus 1, and divide by 2h. So, I take this 2h to here and give you the coefficients. The coefficients are minus 3, 4, 1, 4 minus 1. Similarly, double derivative, I just derived it at the point I using I plus 1 and I plus 2. Well, it turns out the double derivative is same. Double derivative again, for you are using only 3 points. So, double derivative here, here and here are equal. It is quadratic, the way linear. So, when I did the first derivative, my first derivative here and here were equal. So, second derivative at 3 points will be equal, and that is why is 1 minus 2 1. Now, this is called backward formula. So, I want to compute derivative at I but using the points left of me or behind me. So, it is minus 1 and 1. This is again you can see in that. So, this formula corresponds to this guy. So, behind me. So, the where you are is 3, then minus 4 and 1 is symmetric actually, is symmetric of this with the opposite sign, and that is what you got, 3 minus 4 1. So, I hope you understand how to read this table. Now, this is not well, now this is there some new stuff, this is using 5 points, this I did not derive it right now. If you want to use 5 points, then this is what you should use, 1 minus 8 0 8 1. Using 3 points I derived it, this one in fact this formula, but with 5 points this is what you get. And double derivative is this, it is more work, and but you can get this formula. What is the error? So, this column tells you the error. So, you can derive some errors from here. So, how do you get error for this formula? So, let us try to estimate how do you get error. So, somebody says, well, this is the formula I am using. So, the way to, well, that one simple way to do it is fx minus fx minus h. This is what is right, this way, equal to, I use Taylor series. So, fx will remain as it is, minus fx minus h f prime of x. Now, the next order term is h squared by 2 double derivative. I will stop, I mean there are higher order terms, but my error is here. This will cancel and I get h f prime of x plus h squared by 2. Thank you. So, you divide by h, that is what we got here. If I divide by h, so f prime numerical is f prime, which is real value, minus h by 2. Okay, so this is easy, this is just a simple analysis. Now, if my function was linear, this was 0. So, that's why it was exact. If function is quadratic, then I get error right away, and h is a big error. Okay, order linear, this is called linear error. Order h is huge and you should avoid it. H will be typically small, okay. So, like what Newton prescribed, h should be small. So, this is order h. Now, I will not derive this, is order h squared. So, you can do similar ways, but I will give you another scheme, another method derivation in a minute. So, this table you can, we just read from here. Now, so which is best here in this table? h4. So, first derivative h4, you should use 5 points. Okay, now, it is more work in while coding, but it is not much more work. So, if you use 5 points, you get accurate results. You can use 7 points, you can get more. Okay, so, you can derive this formula another way. Now, this is a Q derivation. Some of these ideas, well, by the way, there are more sophisticated way to compute derivatives, higher orders. In fact, a lot of computations of PDEs, partial differential equation, like all the fluid flows, Schrodinger equation, electrodynamic solvers, right? EM solver is derivatives, and people need accurate derivatives. So, there is another scheme which is called compact scheme. I won't have time in this class. So, there are very sophisticated schemes to get very good derivatives, but this will give you an idea how you can get formulas, derived formulas. So, let us imagine that I want to compute derivative, first order derivative, and also estimate the formula error. So, I have choose 3 points, I choose these 3 points again with equal interval. So, my points are x minus h, x and x plus h. So, I will do a Taylor series of this, and so if I do Taylor series, I will get this expression, right. Should I go one by one? I mean, this is the first derivative term is coming from both of these, second derivative will come from again, and third derivative will antisymmetric. Okay. So, this is exact formula for Taylor series to cubic order, and HOT means higher order terms. Now, I want the first derivative. So, what should I do? I should set this to 0. Okay. So, I want this expression, c minus a should be 1 by h, c minus a is 1 by h, and c plus a must be 0. I want accurate up to second order, h squared. Okay. So, set these then what will I get? I will get f prime x, ignore this term. So I keep, if I delete this, I equate this to this, so set this to 0, this equal to 1 by h, so this becomes 1 and this is 0. So I get a formula for f prime x. So these three expressions will give you what are the values of the coefficients a, b, c. So b is 0, c is half and a is minus half. So that is central difference scheme. So the formula is, and what is the error? Error is here. This is the error which I am not including in the formula. So c minus a h cube by 6. So c minus a is 1 by h. So h, so basically you get h squared by 6 f triple prime. That means cubic third order derivative. So I, okay, am I too fast? The slides do tend to get too fast. So using 3 points I want to derive a formula for f prime x, and that is what I have done here. I just equate with the Taylor series and set appropriate terms to 0. So this is the formula I get, and also I get error right away. The term which I ignored, which is c minus a h cube by 6, is that. So error is of what order in central difference scheme? H squared, and forward difference scheme with it was h. This was h, and this was, in fact this is h squared. Now how many numerical operations were you doing here? Numerical operation is addition, subtraction and division. So there is one division involved here, and well, I mean there are two subtraction if you like, or if h is given to you, there is only one subtraction. So the operation is exactly same in these two, but this gives you h squared and this gives you h. So which we should do? I mean never apply this. This is what Newton said, but no, we should not obey Newton for this, we should do that. Okay. So this is how we get this. So I mean this, of course I just derived it here. Okay, so let us do one exercise. Computer code is easy, so I think I will skip computer code. I just wrote a simple code, but you can write a code now. I mean, given a function, you can compute derivative. So the exercise I will give is exponential x. Compute derivative at x equal to 0 using forward difference scheme, central difference scheme, and backward difference scheme, both first order and second order derivative. So this I will not show you how to do the computer code. I mean this Python is straightforward, you just implement this, you will get it. You can vary h and see how the error changes. One thing I will request is that we keep decreasing h. So I want to compute e to the power x derivative of this at x equal to 0. So take 2 points, this is x equal to 0, and then vary h. So function goes like that. No? So derivative here is 1. In fact it should be going like that 1. Now if I vary h, I will get better and better accuracy. So you verify this by doing different schemes and get the error. Central difference scheme should give you h squared. So use h, different h, and fit. Okay.